The first couple of sessions of the physics lab, they are going to serve as an introduction into the error analysis methods, which you are going to encounter whenever you are solving a lab report. But what do we understand by the error analysis in the first place? 99% of the times, an experimental measurement is going to carry on it a certain amount of uncertainty. An uncertainty implies an error. So whenever you see the word uncertainty in a lab report, whether it has to do with physics, biology, or chemistry, uncertainty implies a certain margin of error. So every experimental measurement is going to carry on it a certain margin of error. And the errors in that case, they can be of two different kinds. We can distinguish the random errors and we can distinguish systematic errors. So first off, we can start by defining the uncertainties to be a certain type of errors. And errors in that case, they can be actually split into two different categories. We can distinguish the random errors and we can distinguish the systematic errors. Starting with the case of the random errors. The random errors are actually attributed to unknown causes, meaning that you cannot specify their origin nor identify them, and therefore you cannot eliminate such type of errors in order to render your experiment much more accurate. So you cannot identify them, and therefore you cannot eliminate them. Whereas in the case of the systematic errors, we can distinguish in that category three different subcategories, which are the observational errors, the instrumental errors, and the environmental errors. So starting with the first subcategory within the systematic errors, which is called the observational errors. So what are the observational errors? The observational errors, they are human-related errors, meaning that they are errors that can be due to error in reading the scale, or an error in doing timely measurements, and so on and so forth. So such errors, they actually depend on the type of the experiment that you are performing. They are going to vary from one experiment to another. And they are strictly human-related errors, such as, like I said before, error in reading the scale or an error in doing timely measurements, for example. Then we have the second subcategory within the systematic errors, which is called the instrumental errors. So the instrumental errors, they are errors that are strictly related to the apparatus that you are using. For example, they can be attributed to poor calibration of the apparatus, or they can be attributed to any defect that the apparatus can embody. So whenever you are dealing with an apparatus that has a certain malfunction in it, you can define that to be as an instrumental error. And finally, we have the third subcategory within the systematic errors, which is called the environmental error. So the environmental errors, they are actually related to external conditions. For example, let's say you are working in a room which is not well isolated from the surrounding environment. Therefore, any outside temperature, it can affect your experiment. Moreover, the presence of an air conditioner, the presence of a heater, the presence of a magnetic field or an electric field, or the presence of a humidity within a room, they can also be considered as external conditions, or simply they can fall under the category of environmental errors. Now, unlike the case of the random errors, the systematic errors, they can actually be defined, or they can actually be traced, and therefore eliminated or at least reduced in order to enhance the performance of your experiment. So in the case of the random errors, we said before that they cannot be actually traced, they cannot be identified, whereas the systematic errors, they can be identified and they can be eliminated in order to improve the quality of your experiment. Now, all of these errors combined, whether the random errors or the systematic errors, in addition to the type of the problem that you are solving in a lab report, we can distinguish three main mathematical models, or three main statistical models, which actually help you in determining the amount of error on your experimental results. So what are actually these models? For instance, we can distinguish over here the standard deviation and the standard error. So what's the standard deviation? The standard deviation is a mathematical model which actually shows you how a set of values are going to be varying around their average value. So over here, let's say you have a set of numbers that all belong to one physical quantity. And then you want to find the average value of these set of numbers. Then you are going to check how these set of numbers are going to be varying around their average value. In other words, you are going to be determining the average deviation between these set of numbers and their average value. And then over here you have the standard error. The standard error in that case is going to be a measure of precision. So it's going to be a quantity which is going to be related to the standard deviation, but that quantity over here is going to show you the precision on your average value, like how precise the estimate of your average value is. Then you have the linear regression method, which is the second mathematical model, or the second statistical model. Now, the name of the linear regression is actually pretty indicative of its role, of its purpose. The purpose of the linear regression over here is actually to study the linear relationship between two variables, x and y. So let's say you have two parameters, x and y. You want to study if the relationship relating x and y is actually a straight line relationship. Then, after proving that that relationship is a straight line, you are going to be determining the slope of that straight line and the error on that slope. And finally, we have the third mathematical model, which is called the propagation of error. Now, in the case of the propagation of error, we are going to consider that we have a function. We have a main function or a main parameter that we are going to call it a function. For example, let's consider that main function to be f, or the parameter to be f. It's an arbitrary parameter. But moreover, that main function is actually a function of two variables, for example. It's a function of x and a function of y. So that main parameter, it depends on two random variables. Why do we call them variables? Because we are going to consider that on each parameter we have an error. So alpha over here, the symbol alpha, it denotes an error. From now on, we are going to be representing an error with the symbol alpha. So on that parameter y, you have a certain amount of error alpha y. And then on that parameter x, we have a certain error alpha x. Therefore, x and y would be labeled as variables. They are no longer constants. So over here, we have a function of two different variables, x and y. So in that case, the error on f is going to be what? The error on f is going to be dependent on the errors on x and y, meaning that the error on x and y is going to propagate. It's going to add up in order to form a new error on the main function f. And in order to find the error on the main function f, we are going to be doing partial derivatives of f with respect to the first variable x and with respect to the second variable, which is y. And later on, we are going to be dealing with that case in depth. Now, for the first lab session today, we are going to be strictly talking about the standard deviation and the standard error, in addition to introducing notions like the significant figures and accuracy and precision. Whereas when it comes to the linear regression and the propagation of error, we are going to be leaving it to the second session for next week. So today we are going to begin by explaining about standard deviation and the standard error. So moving on to the standard deviation and the standard error. In this part, we are going to be explaining the notion behind the standard deviation. So what does a standard deviation actually measure? And then we are going to be making the link, we are going to be establishing the relationship which is going to relate standard error to the standard deviation. Noting that the standard error over here, we can refer to it as a root mean squared error. So the standard error, we can refer to it as a root mean squared error, or simply we can refer to it as an error on the average. So, starting with the definition of standard deviation. What's a standard deviation? Standard deviation is a measure of variability of a data set around the average value of that data set. Meaning that the standard deviation, it actually calculates a certain value. And that value calculated is going to be none other but an amount of deviation. But that amount of deviation is going to be between what and what? That amount of deviation, as I have said previously, is going to be between a set of numbers and the average value of these set of numbers. So basically, the standard deviation, it's going to showcase, it's going to show you how a set of numbers are going to be varying around their average value. So it's going to show you the variability of a set of numbers around the average value of these set of numbers. Are they going to be varying right around the average, or are they going to be varying further away from the average? So over here we can add another definition for the standard deviation to be a measure of the amount of deviation. So like I said, it's the amount of deviation between a set of values and the average value of these set of values. So over here what we are going to do next is we are going to find a way in order to calculate that amount of deviation between a data set and the average value of that data set by applying the standard deviation equation. But first off, what do we understand by data set? In order to answer all of these questions, we are going to begin by giving an example, a simple example. We are going to consider that we have a certain parameter x. X, it can be any physical quantity. It can be the speed of light, the speed of sound, volume, pressure, you name it. It can be any physical quantity. And the purpose is to conduct an experiment on x in order to determine several measurements for it. So let's say you ended up with the following results for x. So you have x1 equal to 3, you have x2 equal to 6, you have x3 equal to 9, and x4 equal to 12. So over here we have the term data set. What do we understand by data set? Over here we have several measurements that all belong, that can all be attributed to the same physical quantity, which is x. So whenever you have a set of measurements or a set of numbers that can be attributed to one physical quantity, in that case, that entire population, that entire collection of data over here, it can be referred to as a data set. So over here, the collection of these numbers, we can refer to them as a data set. And in that case, each individual value alone, we can refer to it as a data point. So that entire population, that entire collection, we refer to it as a data set, while each point individually would be a data point. Now going back to the definition, the standard deviation is what? It's a measure of variability of a data set around the average value. The average value of what? Of that entire data set. So the first step is going to be to find the average value of that data set. So in that case, x bar, which denotes the average, is going to be equal to summation of all the xi's, where the subscript I is actually refers to the order of the measurement. So I, it can go from 1 until n number of trials, divided by the total number of trials n. So over here we have 4 measurements. So I, it goes from 1 until 4. So in the case, x bar is equal to x1 plus x2 plus x3 plus x4 divided by 4, which is equal to x bar equal to 3 plus 6 plus 9 plus 12 over 4, which is equal to 9, 18, 30, 30 over 4, which is none other but 7.5. So x bar is equal to 7.5. So over here we have the average, which is 7.5 of that entire collection, of that entire population. So far, we have defined what a data set is, and we have determined the average value of that data set. What's left is what? What's left is actually determining the amount of deviation. We need to be determining that amount of deviation between that entire collection of points and the average value that we have over here. However, when we say the term deviation, the very first thing that comes to mind is actually the difference. Whenever you think of deviation, you are going to think of difference either between two values or two set of values. So over here what we are going to do next is we are going to find the differences between each data point and x bar, meaning we are going to find the difference between x1 and x bar, then x2 minus x bar, then x3 minus x bar, then x4 minus x bar, etc. over here, we are going to be writing down the differences. We are going to start by x1 minus x bar, which is equal to 3 minus 7.5, which is equal to minus 4.5. Then we have x2 minus x bar, which is equal to 6 minus 7.5, which is equal to minus 1.5. Then we have the third difference, x3 minus x bar, which is equal to 9 minus 7.5, which is equal to 1.5. And finally we have the final difference, x4 minus x bar, which is equal to 12 minus 7.5, which is going to be equal to 4.5. So, over here we have determined the deviations or the differences between each data point and the average value over there. However, the target is what? The target is to find the average deviation between that entire data set and x bar. And the purpose is not to find the deviation between each individual point and x bar, but rather the average deviation of that entire data set around x bar. So in that case, what we need to do is we need to find the average deviation of these entire differences over here. So what we need to do next is actually what? Summing all the differences up and divide them by the total number of trials. However, if we look over here, we have a minus sign. And we need to get rid of that negative sign. Over here we have negative 4.5 and negative 1.5, because whenever we are finding a deviation, which is basically a distance, that distance is a scalar quantity, meaning it's a magnitude, so it has to be positive. So in that case, we are going to be squaring each difference before we sum it up. So over here we are going to take the square of the first difference, then the square of the second difference, then the square of the third one, and the square of the fourth one. Now after taking the squares over here, now we are going to be summing all the differences up, all the square differences up, and divide them by the total number of trials, since we eliminated the negative sign. So, in that case, we have x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared plus x4 minus x bar squared divided by the total number of trials, which is in that case 4, which is equal to, let me bring a calculator in order to calculate the values that you have. So over here we have 4.5 squared, which is equal to 20.25 plus 1.5 squared over here, which is equal to 2.25 plus also 1.5, which is 2.25. And finally we have also 4.5 squared, which is 20.25 divided by 4. So let's sum all of these numbers up. So 20.25 times 2 plus 2.25 times 2 divided by 4, which is going to be equal to 11.25. So the final answer is actually 11.25. However, what do we think we have determined in that case? Did we actually determine the average deviation from the mean? Because you have to keep in mind that initially when we found the differences or deviations, we had negative signs. So to get rid of the negative signs, we had to square each number. So in that case, what we are finding over here is no longer the average deviation from the mean, but rather we are finding the average deviation from the mean squared. In other words, we are finding a quantity which is called the variance. So the definition over here is going to be none other but the average deviation from the mean squared, which is none other but a quantity which we call it to be the variance. So to repeat myself. First off, over here we said that we need to find the average deviation between that entire data set and the mean. So to find the deviation, we said that we need to find first off each difference or each deviation between each data point and the average, which we have done over here. However, we obtained negative values over here, and we had to get rid of the negative values since we are basically finding a distance. The deviation is none other but a distance. So to get rid of that deviation, we had to square each term. But by squaring each term, we have actually changed the definition of what we are finding. We are no longer finding simply the average deviation from the mean, but rather we are finding the average deviation from the mean squared, which is none other but a statistical quantity which is called the variance. So, in that case, to find the deviation between that entire collection and x bar over here, what we need to do is actually taking the square root of that entire equation. So simply we have to take the square root of the variance. So the standard deviation is by definition equal to the square root of the variance. So in that case, standard deviation is going to be equal to square root of the variance, which is going to be equal to square root of that equation above, x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared plus x4 minus x bar squared divided by the total number of trials, which is 4. So it's equal to square root of 11.25, which is going to be equal to 3.35. So the standard deviation is actually equal to 3.35, and we are going to refer to that standard deviation with the symbol sigma. So the standard deviation is always being referred to with that symbol sigma over. So that value is actually indicative of what? That value that we have obtained over here is actually indicative of the average amount of deviation. You have to pay attention to the wording. It's an average amount of deviation between that entire data set and the average value x bar. Meaning that on average, each point we expect it to be located at around 3.35 from x bar. But later on we are going to find out that this is not going to be a pretty accurate definition, but rather it's going to be defined as an average deviation of the entire data set and not of each value individually. Now, let's consider that over here we don't actually have only 4 measurements for which we need to find the standard deviation, but rather we have hundreds of measurements for which we need to find the standard deviation. In that case, we need to be generalizing that equation of the standard deviation in order to fit an amount of trials, an amount of samples, or an amount of measurements. So in that case, the general equation of standard deviation is going to be sigma equal to, first off, over here we have the square root, so we are going to start by including the square root. Then over here we have what? Over here we have summation of the differences squared. So over here we are going to start by writing down the symbol of the summation. And that summation in that case is going to go from I equal to 1. Like I said, I, it represents the order of the trial. So I, it goes from 1 until n number of trials or n number of samples. Summation of what? We open the parentheses, summation of each individual value or each individual sample that we have, xi, minus what? minus the common term that we have over here, which is the average value, which is x bar. So xi minus x bar squared, divided by the total number of trials, which is n. And that would be the general equation of the standard deviation if you have n number of trials that you need to account for. And that equation of the standard deviation, we are going to label it as the standard deviation of the population. Why of the population? Because we are taking into account the entire number of trials n. We are not leaving any measurement out, but rather we are taking the entire number of trials into account. Therefore, we refer to that equation as the standard deviation of the population, which has an order n. So the order of that standard deviation is actually n, simply because we are taking into account the entire number of trials, or the entire population that we have. Now in some textbooks, you might see a different equation for the standard deviation. Different how? Instead of having n in the denominator, you are going to have n minus 1. So the difference in that case is going to be that we are no longer finding the standard deviation of the population, but rather in that case we are finding the standard deviation of a sample which is taken out of that population. So in that case, the equation becomes sigma of order n minus 1. So we are no longer at order n, but rather at order n minus 1, equal to summation of xi minus x bar squared, where I goes from 1 until n minus 1, divided by n minus 1 trial, and square root for that entire equation. So as we can see over here, we are no longer taking the entire population into account, but rather we are considering a sample of n minus 1 trials out of the entire population, and therefore we refer to that equation as a standard deviation of the sample which is taken out of the population, and the order of the standard deviation in that case is going to be of order n minus 1. Now when it comes to the physics lab, we are always going to stick to the first equation, which is the standard deviation of the population, because we are always going to take into account the entire number of data points that we have. So we are always going to be applying that equation over here, sigma n, which refers to the standard deviation of the population. Now, depending on the value of sigma over here, we can distinguish two different cases. The cases where the data set has a low standard deviation, and another case where the data set has a high standard deviation or a large standard deviation. So depending on the value of sigma, there are two different cases that we can distinguish. A case where the data set has a low standard deviation, and the second case where the data set has a large standard deviation. What would be the difference in that case? In order to understand the difference, we are going to consider two horizontal axes, and on these axes we are going to be actually arranging some arbitrary points around the mean. So let's consider that first horizontal axis, and over here the second horizontal axis. And in the middle of each axis, we are going to consider the average value x bar. And then around x bar, for the first axis, we are going to be actually scattering whatever data set that we have. We are not going to take like very precise points on that horizontal axis, but rather arbitrary points. However, we are going to consider that for the first axis, for the first horizontal axis, the data set is actually scattered in such a way to be located right around the mean, meaning that the average deviation between the data points and the average value is not that big. So let's consider that over here we have the first data point x1. Let's say over here we have the second data point x2. Over here we have the third data point x3, and over here we have x4. So as we can see over here, the data set that we have is actually scattered in such a way to be clustered right around the average. So it's actually deviated by not a big of a margin around the average, but rather it's actually varying right around the average. So in that case, we refer to that data set as having a low standard deviation, and therefore it has a low degree of variability. Because if you remember before, we have defined the standard deviation to be a measure of variability of a data set. So since over here we have a low standard deviation, therefore that data set has a low degree of variability. So over here, the data set has a low degree of variability, meaning that we have a low measure of variability, or standard deviation has a low measure of variability. So standard deviation has a low measure of variability. Now regarding the second case, for the second horizontal axis, now we are going to consider that our data points are varying further away from the mean. So now the average deviation between the entire data set and the mean, it grew larger. So let's say over here now you have x1, over here let's say you have x2, over here you have x3, and over here you have x4. So by comparison between these two axes, we can clearly see now that the average deviation between the entire data set and that average value grew bigger. So in that case, we can say that over here the data set, it has a large degree of variability, and therefore the standard deviation, it has a large measure of variability. So over here we can say that the data set, it has a large degree of variability, meaning that the standard deviation, it has a large measure of variability. Because, like we said before, the standard deviation is a measure of variability of a data set around the average value of the data set. So just keep in mind that, depending on the value of sigma, you can obtain two different cases, which are either for the data set to be revolving right around the mean, and therefore we have a low degree of variability, meaning that the standard deviation value is actually small. And then we have a second condition where the data set is going to be actually varying further away from the mean. And in that case, we have a large degree of variability, meaning that the standard deviation now is actually, it actually has a large value, it has a big value. Now, if we go back to our measurement over here, sigma equal to 3.35, what can we conclude about that measurement? What can we imply? What can we infer from that measurement that we have obtained? We can simply over here infer that the value of 3.35 implies that the entire data set is actually being deviated on average by 3.35 from the average, which in our case was 7.5. So on average, that entire data set is actually deviating by 3.35 from 7.5. However, if we look at each point individually, for example, let's say if we consider the first trial, x1, is actually x1 going to be included at a deviation of 3.35 from the average value, meaning that if we add 3.35 to 7.5, and if we subtract 3.35 from 7.5, are we going to find x1 to be included in that interval over here? So, let's clarify. So over here you have the average value, which is 7.5. So x bar equals 7.5, comma, and x bar equal to 7.5. We are going to be subtracting sigma. We are going to be subtracting the standard deviation from that average over here, and we are going to be adding the standard deviation to that average over here. Because like I said before, the standard deviation is going to be an indication of the amount of deviation between the entire data set and the mean. Meaning that if you subtract or if you add the standard deviation to the average value, logically you would think that you are going to obtain all the data set to be varying within that interval. But in reality, it's not going to be the case. So let's subtract over here 3.35, and let's add over here 3.35. So as we can see now, we have an interval which consists of x bar minus sigma and x bar plus sigma. So that first interval over here is going to give you a value of 4 point something. And that other branch of that interval over here is going, or that other end of that interval over here is going to give you a value of 10 point something. So if we bring the first data point, x1 equal to 3, we can clearly see that x1 equal to 3 actually does not belong to that interval. So the first data point is not varying at a distance of plus minus 1 sigma from the mean, but rather that first data point is actually varying at a certain distance of plus minus 2 times sigma from the mean. So now we can distinguish over here several intervals that all consist of the standard deviation and the average value. However, the order of the standard deviation, not the order, but the factor by which you are multiplying the standard deviation is going to change from one interval to another. So in that case, x1 is going to be actually located in the interval x bar minus 2 times sigma. So over here we have multiplied 3.35 by 2, and then we have the other end of the interval, which is x bar plus 2 times sigma. So 2 times 3.35. Whereas over here we had x bar minus sigma, and over here we had x bar plus sigma. And the same thing, let's say if we consider the fourth point, x4 equal to 12. x4 equal to 12 also, it does not belong to that interval, x bar minus sigma and x bar plus sigma, but rather it can be found now in a certain interval, which is x bar, let's say, minus 2 times sigma, or x bar minus 3 times sigma and x bar plus 3 times sigma. So the point behind all of these intervals is actually to find a certain margin, to find a certain range where your entire data points over here are going to be included. Are they all going to be included in x bar minus 1 sigma and x bar plus 1 sigma? Or are they going to be included in x bar minus 2 times sigma or x bar plus 2 times sigma? Or are they going to be included in x bar minus 3 times sigma and x bar plus 3 times sigma, etc.? In theory, they say that 68% of your data points are usually found in that first interval, x bar minus sigma and x bar plus sigma, and up to 95% of your data points are usually found in x bar minus 2 times sigma and x bar plus 2 times sigma, and up to 100% or 98% of your data points are found in x bar minus 3 times sigma and x bar plus 3 times sigma. So what we actually mean by these percentages, if you were doing a questionnaire, and let's say you have 1,000 samples, and you want to find the mean of your samples, and then you want to find the standard deviation between the entire sample and the mean. In that case, you are going to be checking within which interval or within which deviation from the mean your entire data points are going to be included. Are they going to be included at a deviation of plus minus 1 sigma from the mean, or are they going to be included within a deviation of plus minus 2 times sigma from the mean, or are they going to be included at a certain deviation of plus minus 3 times sigma from the mean? So by theory, they say that 68% of the data points are usually found in x bar minus sigma, x bar plus sigma. Up to 95% of the data points are found in x bar minus 2 times sigma and x bar plus 2 times sigma. And up to 98% or 100% of data points are usually found varying within a certain deviation of plus minus 3 times sigma from the mean. So over here, up to 95% are varying within a certain deviation of plus minus 2 times sigma from the mean. And over here, 68% of the results are varying within a deviation of plus minus 1 sigma from the mean. Now, these notions, you are not going to encounter them in any lab report, but rather you are going to see them in a different manner when it comes later on to finding the standard error. In that case, we are going to be dealing with such intervals. But when it comes to the standard deviation, you are not going to be dealing directly with such problems. Let's move on. Now we are going to move on to do another example, which is going to be related strictly to physics, where you are going to be applying the standard deviation, and in order to understand the notion behind it quite better when it comes to physics problems. So we are going to be solving the following problem, which is actually a problem related to magnetism. So some of you, like some of the labs that you are taking, they are not going to involve any hint of magnetism, but rather they are going to be purely classical. However, it's a general example which help you to understand the general concept behind the standard deviation when it comes to be applicable to physics problems. So over here, for example, let's say we have a solenoid, and you are applying a certain electrical current to that solenoid. But each time you apply an electrical current, you are actually going to be measuring the corresponding magnetic field. So let's say over here you apply the current of 1 amps, then you measure a certain magnetic field of 2 Tesla, then you change the current to 3, over here you obtained a certain value of 5, then you change the current to 4, you obtained a certain value of 8, then over here you change the current to 7, and you obtain a certain value of 12 Tesla. So each time you are applying an electrical current to that solenoid, you are actually determining the corresponding magnetic field. Now over here we have a third parameter, which is an unknown, which is the number of turns of a solenoid. So the shape of a solenoid is basically like that. It's basically a copper of wire wrapped in many turns. So it has a certain specific number of turns, and we want to determine that number of turns. Now for such problems, for such standard deviation problems, the first question is always going to be similar. It's actually very common among all the types of standard deviation problems. The first question will be of the following manner. Establish the relationship between the magnetic field, the electrical current, and the number of turns. So you want to establish the equation relating all 3 parameters. In that case, the magnetic field is given as B equal to mu0 and I over the length, where mu0 is actually, it's a magnetic constant. It's the permeability of free space. It's an indication of the ability of free space to support magnetism. And N over here would be the number of turns, I would be the current, the electrical current applied, and N would be none other but the length of that solenoid. So let's say that the length and the mu0, they are given. They are already given. The values are already given. And you still have to find only the number of turns. So in that case, moving on to the second question. In the second question, they say that you need to complete the table, and then you need to find the average value of the number of turns. So over here, we already have values for B. We already have values for the current. We are still left to find values for the number of turns. So in that case, the number of turns are equal to the length times the magnetic field over mu0 times R. So over here we start by finding each number of turns. So N1 is equal to L times B1, B1 which is the first value over here, divided by mu0 times I1, I1 which is the first value of the current. Then N2 would be equal to L times B2, which is 5, over mu0 times I2, which is 3. And then the same thing for the third trial, N3 equal to L times B3 over mu0 times I3, and N4 equal to L times B4 times mu0 times over mu0 times I4. So After finding each individual value of the number of terms, what we are going to do next is to find the average value of the number of terms. In that case, the average value would be n bar equal to summation of all the ni's divided by the total number of trials. So n bar is equal to n1 plus n2 plus n3 plus n4 divided by 4. And then you find the average. You carry on and you find the average value of the number of terms. Then we have the third question over here. And the third question, they are asking you to determine the standard deviation of the number of terms of the data set. So over here we have that entire data set of the number of terms, and we want to determine the standard deviation, meaning we want to find the standard deviation of the population. So in that case, going back to the previous example, if you remember, we started by finding the difference between each individual value and the average value over here. So we are going to start by finding the differences. So we start by finding n1 minus n bar, then n2 minus n bar, n3 minus n bar, and n4 minus n bar. But if you remember, we have to get rid of any minus sign that we might obtain in those differences. So in that case, we are going to be directly squaring each difference. So over here, we are going to take the first difference squared, then the second difference squared, then the third one squared, and the fourth one squared. And finally, you apply the standard deviation equation. So you take, you are going to sum up all of these differences squared, you are going to divide them by the total number of trials, and then you are going to take their square root. And therefore, the standard deviation of that number of terms over here is going to be n1 minus n bar squared plus n2 minus n bar squared plus n3 minus n bar squared plus n4 minus n bar squared divided by the total number of trials, which is 4. Over here, you have to keep in mind that if we keep that equation without a square root, we are actually finding the variance, which is the average deviation squared. But our aim is to find simply the average deviation. So in that case, we are going to be taking the square root of the entire equation. And that will be the standard deviation of the number of terms data set. Now, by finding the standard deviation over here, we are actually finding what? We are actually finding an estimate of the measure of variability of the data set around the average value of the data set. So as we have said before, the standard deviation is a measure of variability. So that measure of variability is simply going to tell you if your data set is actually varying right around the mean, meaning it has a low degree of variability, or if the data set is actually varying further away from the mean, meaning it has a large degree of variability. But the standard deviation is not going to comment on the precision of your result, meaning that if you were to tweak the conditions of that experiment, let's say if you were to eliminate the systematic errors completely, in that case, each value obtained for the magnetic field is going to change, and therefore each value of the number of turns is going to change, and as a result of that, the average value over here is going to change as well. So in that case, the standard deviation is not going to be indicative of how precise that average value is, or how precise that average deviation between the data set and the average value is. In that case, we need to be introducing another parameter, which is going to be the standard error. So what's the standard error? The standard error is actually a measure of how precise the estimate of a data set is. So what's the estimate in the case? The estimate is going to be none other but that average value. And the standard error is strictly dependent on the sample size. So what do we mean by the sample size? So let's start. The standard error is is a measure of how precise the estimate of a data set is. So like I said, the estimate is actually what? The estimate in our case is going to be none other but the average. Why is it an estimate? Because like I said before, if you were to change the conditions of the experiment, that average value over here is going to change. So what we are actually obtaining over here is an estimate of what the real value or of what the average value should look like. So the standard error is simply a measure of how precise the estimate of a data set is, whereas standard deviation is a measure of variability of a data set. And like I said before, the standard error is going to be dependent on the sample size. So what do we mean by the sample size? The sample size is simply the number of measurements that we have. So over here we only have 4 measurements. So the bigger the sample size is, therefore the smaller the standard error is going to be. Because mathematically, the standard error, or you can call it the root mean squared error, or the error on the average, is given as alpha equal to, so the symbol of the standard error is alpha, alpha equal to the standard deviation sigma, so sigma over here is the standard deviation, divided by square root n. Alright? So as you can see over here, the standard error is actually dependent on the sample size, meaning that if you were to increase the sample size, let's say from 10 trials up to 1,000 trials, therefore the standard error is going to decrease, which is actually logical, because whenever you are increasing your number of trials, therefore you are approaching the right estimate that you need to approach. You are approaching the expected value that you need actually to reach, or that you can expect from that experiment. So as we can see over here, the standard error and the sample size, they are inversely proportional to each other. But moreover, that standard error is actually dependent on the standard deviation, sigma. So whenever you obtain the value of the standard deviation, sigma over here, simply by dividing it by square root n, you can obtain the standard error, which is going to be, in that case, the error on the average, or the error on the deviation. Now, over here we need to point one thing, that the denominator in the error is going to be dependent on the order of sigma. So before we saw that we have two orders of sigma. We have sigma n, which is for the population, and you have sigma n minus 1, which is for the sample. In that case, if we were using over here sigma n, if we were using the value that we have obtained over here for sigma n, meaning the standard deviation of the population, therefore alpha is going to be divided by square root n minus 1. So over here we have alpha equal to sigma n divided by square root n minus 1. Whereas if we were using the standard deviation for the sample, therefore the error is going to be sigma n minus 1 divided by square root n. But both equations are going to yield the same result. But you have to keep in mind that you should know which order of sigma you are using in order to manipulate with the order of the denominator. So if you have sigma n in the numerator, therefore you are going to divide by sigma n minus 1. If you have sigma n minus 1 in the denominator, therefore you have to divide by sigma n in order to get the value of the error. And like I said, both equations are going to yield the same result. But you have to keep in mind which order of sigma you are using in that case. Moving on now to much simpler notions, such as significant figures. What do we understand by the significant figures? The significant figures is actually based on the number of digits that make up a number. So by counting the number of digits that make up a number, you would actually be defining the number of significant figures in a number. So for example, let's consider 8, 0.8, 0.08, 800 times 10 to the power 2, and 0.01008. So starting with the first value over here. Since over here we have only one digit, which is 8, therefore we can say that that number consists of one significant figure. Over here we have 0.8. You might immediately say that we have 2 digits, so therefore we have 2 significant figures. But no. Whenever you have a number which begins with strictly zeros, therefore the zeros are not counted as part of the significant figure. So as long as the leading digit is going to be 0, therefore we are not going to count it as part of the significant figure, but rather we are going to count from the digit which is different than 0. So in that case, that entire number over here, it consists of one significant figure. The same thing over here. We have a leading digit of 0, followed by another digit which is 0, then followed by 8, which is different than 0. So we start counting from 8. Therefore, that entire number over here, it consists of one significant figure. The same thing over here. No, over here it's different. Over here we have 800 times 10 to the power 2. However, the power is never counted as part of the significant figures. So over here we can say that we have 1, 2, and 3 significant figures. Therefore we have a total of 3 significant figures. And over here you have to keep in mind that the leading digit is actually different than 0. Therefore, it is okay to count the zeros after it as part of the significant figures. So over here we have a total of 3 significant figures, and like I said, the power is not counted as part of the significant figures. And finally, the last example over here, we have a leading digit of 0 followed by another 0, then followed by 1, which is different than 0. In that case, we are going to start counting from 1. So we have 1, 2, 3, 4 significant figures. So for the last number, we have 4 significant figures. How can we apply the significant figures? The significant figures are strictly applicable whenever you are reporting a value of an error. For example, if you are reporting a value for the standard error, which is an error on the average, you are going to be applying the significant figure rule. When you are finding the error on slope, when you are finding the error of propagation, in all of these cases, we are going to be applying the significant figure rule, which is going to be the following. The significant figure rule states that an error should always be reported with one significant figure, with the exception if the leading digit in an error is actually 1 or 2. Therefore, you have to retain 1 digit after 1 and 1 digit after 2. For example, let's say you obtained for an error alpha equal to 4.4789. As we can see over here, we have 1, 2, 3, 4, 5 significant figures. So initially, we have 5 significant figures. But the rule says that you need to be reporting an error with only one significant figure. Therefore, you are going to cancel out the 4, 7, 8, and 9, and you are going to report the answer for the error as alpha equal to 4. Let's say you have alpha equal to 0.5841. So over here we have 1, 2, 3, 4 significant figures. And we need actually to reduce it down to 1. Therefore, we are going to be cancelling out the 8, the 4, and the 1. However, since over here we have a number of 8, which follows 5, therefore we are going to round up. We are going to be rounding 5 up to 6. Therefore, alpha is equal to 0.6, which is a number that consists of only one significant figure. Now regarding the exception to the rule, which is whenever you have a leading digit of 1 or 2 in an error, meaning that, let's say you have alpha equal to 0.1465. And then you have alpha equal to 2.0145. So, over here the leading digit is actually 1. Like I said before, the 0 is not counted as a leading digit. and over here the leading digit is actually 2. There is an exception to the rule that says whenever the leading digit in an error is 1 or 2, therefore you have to retain 1 digit after 1 and 1 digit after 2. Therefore you are reporting the final answer for the error with 2 significant figures instead of 1. Therefore over here you are going to be cancelling out 6 and 5, and over here you are going to be cancelling out the 1, the 4, and the 5. However, since 4 is followed by 6, we are going to be rounding 4 up to 5. Therefore the final answer in that case would be alpha equal to 0.15, which actually consists of 2 significant figures. And over here we are going to report the final answer as alpha equal to 2.0, which also consists of 2 significant figures. And like I said before, that notion for the significant figures is only applicable to errors. Whenever you are reporting a value for the error on the average, meaning you are finding the root mean squared error, or whenever you are finding the error of propagation, which we are going to learn next week, or whenever you are finding the error on slope in the linear regression method. You always report the answer for the error with only 1 significant figure, with the exception if you have a leading digit of 1 or 2, therefore you have to retain another digit after 1 and another digit after 2. Therefore you have a total of 2 significant figures. And always do not forget to include the unit for the error. So whenever you are reporting the final answer, that final answer should be accompanied by the unit of the error, which is going to be the same unit as the main parameter for which you are finding the error. For example, let's say the main parameter is actually gravitational acceleration, which has a unit of meters per second squared. Therefore, the error on that gravitational acceleration is also going to be in meters per second squared. And that would be for the significant figure scope.